Thank you to Carl and to Jessica for organizing this conference. Right. So my goal is to discuss really to give a survey talk, so not a very detailed technical talk, but give a survey of some recent results concerning the vanishing of cohomology for Shimura varieties in certain instances. And what I want to start with is just to give you a brief overview of Shimura varieties, where I'm going to give you a very rough sense for what a Shimura variety is, and then some examples. And then I will discuss a few conjectures about the vanishing of cohomology of Shimura varieties. Then I will state the main theorem about the perfectoid geometry of Shimura varieties, which is what gets used to prove some of these vanishing theorems, and which was sort of discovered and by Peter Schulze. And then I will discuss some results about vanishing of cohomology for completed cohomology. And then I will discuss some results at finite level. All right. And so I'm going to start my talk by considering a pair that consists, that is known as a Shimura datum, and this consists of a connected reductive group over Q, and then a conjugacy class of homomorphisms between this group S, which is known as the Deligne torus, and our group over R. And this pair is called a Shimura datum if it satisfies certain axioms. So I'm not going to give you the axioms, but I should just say, so this group S that shows up here, and it's sort of defined this way, but the reason that we're considering it is because it is the Tanakian group for the category of real Hodge structures. And so you should think of this X, or of the points of X, as corresponding to real Hodge structures. And then one of the key things that these axioms ensure is that you can really view X not just as sort of pointwise giving rise to Hodge structures, but X itself is a variation of Hodge structures, which is a technical notion that, say in particular, means that the Hodge filtration associated with the Hodge structure varies holomorphically. So anyway, you start with a group over Q, and you also have this X, which is a variation of Hodge structures. And then you also choose some level that you can view as some compact open subgroup in the finite adelic points of the group. And this needs to be sufficiently small, and there's a technical condition that's called neat that guarantees that. And so when you have this kind of Shimura data and a sufficiently small level, you can define associated to this an algebraic variety over E, which is known as the Shimura variety attached to G at level K. And so this is an algebraic variety that is defined over some number field E, which is, so it's a finite extension of Q. So an algebraic variety defined over a number field. And if you haven't encountered Shimura varieties before, I should say that one of the things that this does is that when you take the underlying complex manifold, this recovers locally symmetric space attached to G at level K, which is the double quotient X cross the finite adelic points of G, quotiented out by the level K on one side, and then quotiented out by the diagonal action of Q, of G of Q on the other side. Though G of Q acts naturally on X because G of R itself acts on X. And then via the diagonal embedding into G of AF. All right, so a Shimura variety is an algebraic variety defined over a number field, E, which is known as the reflex field, and whose underlying complex manifold is the locally symmetric space attached to G. And so this is about as much as I will say abstractly about Shimura varieties, but I want to give you some examples. So if your group, the group that you start with is GL2, the corresponding X will be the union of the upper and lower half complex planes. And then the corresponding Shimura varieties in that case are modular curves, which are actually defined over the rational numbers over Q. And if you write down the double quotient definition, which is the underlying Riemann surface associated to these curves, then you can decompose that as a more familiar space. So a disjoint union of finitely many copies of the upper half plane, quotiented out by certain gamma I, which are sufficiently small congruence subgroups of SL2Z. So there are subgroups of SL2Z that are cut out by some congruence relation. And there's a general way of, you can think about the complex points of the Shimura variety in this double quotient sense using the adelic interpretation, but you can also sort of write it down in a more perhaps down-to-earth way like this by taking quotients of Hermitian symmetric domains by arithmetic groups. All right, and so I guess this is, for some reason I can't seem to move to my next, there, right. And this is just a picture of, so if you think about SL2Z acting on the upper half plane, then this is how you obtain a fundamental domain for that action. And so this gives you a sense of what the quotient of H by one of these gamma I's might look like. So this would be fundamental domain. So this would give you the quotient of H by SL2Z. And then covers of that would be these modular curves over the complex numbers. All right, and so this is one example I want you to keep in mind. And in fact, so this, what I said in the beginning about the variation of Hodge structures, so what that ensures is that you really have a moduli interpretation for your Shimura variety. So in this case, the modular curves have a moduli interpretation. So they represent a moduli problem defined over Q, which is in terms of elliptic curves equipped with extra structures. Okay, other examples would be GSP2G. If you take your group to be that, and then you take for X to be sort of a higher dimensional generalization of this union of upper and lower half complex planes known as Siegel double space. And then the corresponding Shimura varieties are actually also going to be defined over Q, and they are so-called Siegel modular varieties. They are moduli spaces of principally polarized abelian varieties of dimension G. All right, once you have these GSP Shimura varieties, you can also talk about Shimura varieties of Hodge type. Those are the ones for which you have a closed embedding of your pair GX into Shimura datum G tilde X tilde, which is of Siegel type, so which looks like the one in this example. And so there are quite a lot of Shimura varieties of Hodge type, and just to give you one example, which is in fact even slightly more specific, is for instance something associated to a unitary similitude group. Those in fact are of PL type, so they are moduli spaces of abelian varieties equipped with polarizations, endomorphisms, and level structures. But for the most part, you can study them by just embedding them into the Siegel modular varieties. Then there are Shimura varieties of abelian type, where I don't really want to give you the definition, but I just want to say that these are closely related to Shimura varieties of Hodge type. Essentially, on the level of connected components, if you want to obtain a Shimura variety of abelian type, all you have to do is take a quotient by some finite group. And one example, which is going to show up towards the end of my talk, is basically, if you wanted to think about modular curves, or you wanted to think about the group GL2, which gives rise to modular curves, but you wanted to think about it over a field other than Q, say over a totally real field. Then the corresponding group would be this Weil restriction of scalars from F to Q of GL2. And the corresponding Shimura varieties are called Hilbert modular varieties. And these are Shimura varieties of abelian type. So they're not quite of Hodge type, but they're closely related to them. And essentially, you can prove many things about them by ultimately reducing to this Siegel case. And in all of these examples, you can ultimately relate to some moduli interpretation in terms of abelian varieties that are higher dimensional and possibly equipped with extra structures. And then there's also Shimura varieties that are not even of abelian type, and I'm not really going to say anything about them in this talk, just that there's a classification. And so the examples that give rise to Shimura varieties are of abelian type are, for instance, those that are associated to Dynkin diagrams of types E6 and E7. So there are some Shimura varieties that sort of fit beyond this and that we don't understand nearly as well. All right. So one thing that we're interested in when it comes to Shimura variety is understanding their, say, singular cohomology. So you can look at the underlying complex manifold, and you can look at their either usual or compactly supported cohomology with characteristic zero coefficients. And then you don't just study that cohomology, but in fact, because of this double quotient interpretation in terms of G of AF, it's not too hard to show that you have an action of a Hecke algebra on Shimura varieties, where these Hecke operators act as correspondences, and in turn this gives you an action on the cohomology of the Shimura varieties. So this just generalizes the usual action of Hecke operators on the cohomology of modular curves. And so the reason why we care about this is that it turns out that the systems of Hecke eigenvalues, so the systems of eigenvalues for this algebra that occur in one of these cohomology groups can be described in terms of certain automorphic representations of G. So for example, if you start with GL2 and you're looking at modular curves, then the Eichler-Shimura isomorphism describes the H1 of modular curves in terms of modular forms and cusp forms. So this is something that generalizes. And then I said I wanted to discuss vanishing theorems. And so the starting point is the following theorem or fact maybe about the cohomology in characteristic zero of these Shimura varieties. So if you have maximal ideal in your Hecke algebra, which is essentially going to prescribe to you a system of Hecke eigenvalues, and you have a very strong condition on this Eisenstein maximal, on this maximal ideal, which is this non-Eisenstein condition, then it turns out that you expect that the cohomology of the Shimura variety is only supported in 1 degree. So non-Eisenstein will mean basically there is a residual Galois representation, or there should be a residual Galois representation attached to this system of Hecke eigenvalues, and non-Eisenstein is the assumption that this Galois representation is absolutely irreducible. So for instance, you could think about it as something that, you know, yeah, I guess a residual representation is irreducible. So for modular forms, we have associated Galois representations, and then it makes sense to talk about the semi-simplification of the reduction of the Galois representation. Okay, and so then in characteristic zero, there's this expectation that cohomology will only be supported in 1 degree, and in fact, that degree would be the middle degree in which you can have cohomology. So it will be equal to the dimension of the Shimura variety. And this is something that's predicted by Arthur's conjectures. And basically in many cases, this is something that can be proved using work of Franke and ultimately reducing to a computation of Borel and Wallach for GK cohomology of tempered representations. So for instance, if you started out with a unitary Shimura variety or something like this, you would be able to write down a proof of this fact in characteristic zero that would amount to sort of, yeah, kind of finding the right references. And in fact, you even know this more generally, you know, a more general version of this that applies to locally symmetric spaces that aren't even Shimura varieties. But what I'm interested in the talk is not to discuss the sort of the characteristic zero vanishing theorems, but rather questions and vanishing theorems about cohomology with torsion coefficients. And so in fact, it's enough to consider mod L cohomology, where L is some prime number. And so this is what I'm going to be interested in for the rest of the talk. And so then you might expect that the same result holds true. This non-Eisenstein condition is a condition that you can formulate for the mod L Galois representation. And you might expect that the same sort of thing holds true. And this is something that's conjectured in a paper of Caligari and Garrity, and also in Emerton's ICM talk. Probably goes back before that, but I guess these are the references where this particular conjecture is stated. And you might ask, okay, why would you expect something like this? And so one reason is, okay, so I said that in characteristic 0, this kind of vanishing result is predicted by Arthur's conjectures. And these days, now that we know, for instance, the existence of Galois representations attached to torsion classes, we're really moving towards understanding what a mod L Langlands program might mean. And so if you want to formulate a mod L analog of Arthur's conjectures, you might expect that something like this holds true, even for this mod L cohomology. And another reason, so in characteristic 0, it's essentially known. Another reason why you might expect something like this to hold true more generally is that you can actually prove it in low dimensional cases. For instance, for the cohomology of modular curves. And there are also quite a lot of partial results towards this kind of vanishing theorem. And I guess that the ones that I want to mention right now are due to Lan and Su, which are quite general, but only work for sort of in the case where the Shimura variety has good reduction at L and where the weight is sufficiently regular. So maybe they don't always work with constant coefficients, but with twisted coefficients that have to satisfy some regularity assumption. And then there's also results of Emerton G for U21 Shimura varieties, of Shin, for Harris-Taylor Shimura varieties, and of Boyer, also in the Harris-Taylor case. Okay, and another thing that I want to discuss is what would this kind of result be good for? So there are some reasons to believe it might hold true, and now, if you know it, what can you do with it? And so it turns out in this paper of Caligari-Garrity, they explain a general framework for implementing generalization of the Taylor-Wiles method that works really, without many that should work quite generally. In the case of Shimura varieties, if you want to implement what they do, you really have to do the kind of classical patching due to Taylor-Wiles. And there you need to know that your cohomology is concentrated in 1 degree. So if you want to apply the Taylor-Wiles method for the cohomology of Shimura varieties, then you need to do patching and you need to assume that your cohomology is concentrated in 1 degree. Another thing is this result, even in the case of modular curves, where it's pretty easy to establish, it's actually key, shows up as a key ingredient in Emerton's paper, where he proves the compatibility between the p-adic local Langlands correspondence for GL2QP and the completed cohomology of modular curves, where he needs some projectivity result for completed cohomology over the Iwasawa algebra. And here my prime P is equal to the prime L, where L is the characteristic of these coefficients. So it's useful in the p-adic local Langlands program, and it's also useful in making progress on, say, various instances of the Bloch-Kato conjecture, for instance, improving level raising results or establishing various properties of Kolyvagin systems or Euler systems. Okay, and now I want to discuss, maybe this would be a good place to ask, does anyone have any questions at this point? It's okay if, then I guess I also want to mention a different kind of vanishing result, which is not vanishing for cohomology at finite level, but rather vanishing for completed cohomology. And I want to define a slightly more general version of completed cohomology than maybe what you're used to. So the idea is to look at the cohomology of your Shimura variety. And here, of course, I should have taken the underlying complex manifold. But so you want to take the cohomology of the Shimura variety with mod L coefficients. And in this case, I can just take L equals P. And I want to consider, I am really sorry about this. I guess there is a typo on my slide, so this should be a direct limit, of course. Okay, I guess it depends what kind of cohomology you want to consider, but you want to consider the inverse system of Shimura varieties, where your level at P shrinks. And you can get it to shrink all the way, or you can consider just levels that contain a fixed compact subgroup N0 of GQP. And when N0 is equal to 1, and you consider the inverse system of Shimura varieties, where you take arbitrarily small levels at P, and you consider the relevant system of cohomology groups, you can obtain Emerton's completed cohomology. And when GQP is split, you can also take N to be the unipotent radical of a standard Borel in GQP, and take N0 to be the ZP points of that. And then if you perform this kind of construction for that choice of N0, then what you obtain is not the full completed cohomology, but rather it's something that's very closely related to an earlier construction of HIDA, which is ordinary completed cohomology. So to be completely precise, you need to apply an idempotent to your completed cohomology in order to obtain HIDA's ordinary completed cohomology. But it at least goes in the direction of that. And that studies this is a general way to define p-adic automorphic forms on Shimura variety, this completed cohomology. And then this is a way to study ordinary p-adic automorphic forms, which are roughly the ones for which the corresponding Galois representation is ordinary. So it's upper triangular. And then we expect that there is a vanishing for completed cohomology with compact support whenever I is greater than D. And when N0 is trivial, so when you're looking at really full completed cohomology, then you also expect vanishing of the usual completed cohomology above this middle degree. And so in this case of N0 equals 1, the vanishing of usual cohomology and compactly supported, usual completed cohomology and compactly supported completed cohomology is predicted by a conjecture of Caligari and Emerton, which is in turn motivated by heuristics from the p-adic Langlands program. All right. Are there questions here? All right. So my goal for the rest of the talk is to discuss some results towards these conjectures. And all the results that I will discuss will use the geometry of the Hodge-Tate period morphism. So they're not the only ways to approach these kinds of vanishing conjectures, but sort of this geometry of the Hodge-Tate period morphism has been able to say some quite interesting new things in this setting. And so I want to focus on the results that use that. And they're really theorems that have very different flavors. So vanishing of cohomology at finite level versus vanishing of completed cohomology. But in some sense, the starting point for making progress on both is this Hodge-Tate period morphism. And to talk about it, I need to talk about perfectoid Shimura varieties. And so the first thing that you do is that instead of looking at your Shimura varieties as a complex analytic space, you can think about it as a p-adic analytic space. And so what you want to do is to base change from your reflex field to some completion of your reflex field at some prime above P. and then take the associated adic space in the sense of Huber. And now I've put this star here. So the star denotes the minimal compactification of the Shimura variety. And you can do this construction either for the Shimura variety itself or for the compactification. But we're going to see that in everything that we need to consider, it's important to actually work with something, with a compact space. So, and you can see that Shimura varieties are typically non-compact, even just from the example of modular curves. Okay, then the Shimura datum gives you naturally a Hodge co-character, which is a priori a co-character of your group G, defined over the complex numbers, but in fact, its conjugacy class is defined over this reflex field. And so because of that, if you just sort of such a co-character will define a parabolic subgroup of your group once you've extended your scalars to E. The parabolic subgroup essentially from a co-character, there's two ways to extract a filtration. And you can either look at sort of well, a co-character will naturally give you a grading. And you want to think of that grading as sort of the Hodge decomposition. And you can consider the filtration, that would be the Hodge filtration. And that's one way to get a parabolic, or you can consider the opposite. And I want to consider the opposite. That's what this P mu is. And then I consider the associated flag variety. And I want to take it not just as a algebraic variety, but rather, again, as an adic space over this p-adic field EP. Okay, and so here's the main theorem that we're going to use about the geometry of the Hodge-Tate period morphism. And this is really largely due to Schulze. There's a small piece about identifying the flag variety at the end that is proved in joint work with me. So there exists a perfectoid space, which is the, say, Shimura variety with infinite level at P, and which can be identified in a precise sense with the inverse limit over levels at P of Shimura varieties at this particular level at P. And this equality, to be completely precise, this equality holds true in the category of diamonds. But it is something that is good enough for understanding cohomology. And a morphism of adic spaces. So once you go to the perfectoid Shimura variety, there's also a morphism of adic spaces that takes this to the associated flag variety. And this is the so-called Hodge-Tate period morphism. So the first thing about this Hodge-Tate period morphism that you should know to just get a sense for what it is on points is that in the case of the modular curve, it measures the relative position of the Hodge-Tate filtration on the elliptic curve that is parametrized by that modular curve. So for example, if I take here C to be a perfectoid field and I look at a COC point of my modular curve, which at infinite level, which is going to correspond to an elliptic curve over C and possibly some other structures away from P. And then at P, you will have a trivialization of the Tate module of the elliptic curve. Then this point is going to get mapped to the point on the corresponding flag variety that corresponds to this Lie algebra of E with a Tate twist, which can be seen inside the Tate module after you extend your scalars from ZP to C. So this is one piece of the Hodge-Tate decomposition for E over C. And so I want to view, so yeah, I want to consider this map and note that because the Tate module is trivialized, I can identify the right-hand side canonically using alpha with C squared. And so here I am looking at points on the modular curve at infinite level, and here I'm looking at lines inside two-dimensional vector space. And so this naturally gives you a map from the modular curve at infinite level to adic P1. Of course, what I've described is really just on the level of points, but you can make this into morphism of adic spaces using basically the relative Hodge-Tate filtration. So aversion in families. So that's one thing to know about it. Another thing to know about it is that it's sort of to know how it interacts with the other structures that are present where you have a Shimura variety here. So on one hand, you have an action of a Hecke algebra, and here I'm always considering a Hecke algebra away from P. So there's an action of the Hecke algebra here by correspondences, whereas this is really a purely local object that only knows about our group over QP. And pi Hodge-Tate is equivariant for T in the sense that it's equivariant for the Hecke action here and the trivial action here. On the other hand, if you identify the space with the inverse limit of Shimura varieties at lower levels Kp, and you see you have a natural action of GQP on this tower. And you also have a natural action of GQP on this flag variety. And this Hodge-Tate period morphism is also equivariant for that. And it's essentially by construction. That's something you can check in this case. All right, so the third thing that you need to know about this morphism is that it's aphenoid in the following sense. There is an open cover of the flag variety by aphenoids, UI, such that the preimage of each UI under the Hodge-Tate period morphism is actually an aphenoid perfectoid space. And so, for example, for the modular curve, the flag variety is just P1, and your usual cover of P1 by open unit balls will give you an aphenoid cover that works. All right, and so in particular, you can use this to show that the fibers of the Hodge-Tate period morphism are themselves aphenoid perfectoid spaces as well. Okay, any questions at this point?
There's a question what E1 was. E round parentheses.
This is a Tate twist. So just to be precise, when you consider the Hodge-Tate decomposition, sometimes you want to consider it with a Galois action. And then this Tate twist is remembering that the Galois action gets twisted by the cyclotomic character. But for the most part, you can ignore it. It's just, yeah, I mean, it's right.
And there's another question.
Yeah.
Can the Hodge-Tate period map be defined at the level of schemes?
No, you really need to work with a p-adic analytic space. So you really need to, yeah, basically go to a perfectoid space, which is in particular an adic space. I guess there is an integral. I guess there is an integral version of the Hodge-Tate period map that is considered in a paper of Piloni and Strobe, but that uses a strange integral model of the Shimura variety. And that, I think, is defined on the level of formal schemes. And so you can see some shadow of it that you can use on the level of schemes, but not, yeah, like the morphism that has this property and that, yeah, you really need to go to perfectoid spaces. All right. So now I want to mention some theorems, some vanishing theorems that can be proved using the Hodge-Tate, well, using perfectoid Shimura varieties and the Hodge-Tate period morphism. And so the first thing that I want to say is this conjecture of Caligari and Emerton about vanishing of completed cohomology, where you were really going to infinite level at P. This is now known, and it's a theorem of Scholze and Hansen-Johansen. And this is known in the case of, say, Shimura varieties of abelian type. And it sort of consists of two different parts. One part is for compactly supported cohomology, and that is proved purely by geometric methods. And what you need to prove that theorem is really just to know that the Shimura variety with infinite level at P is a perfectoid space, plus vanishing theorem of, which is really an almost vanishing theorem for the cohomology of O hat plus on an affinoid perfectoid space that vanishes in degree greater than 0. So those are the ingredients that get used in proving this theorem for compactly supported cohomology. For usual cohomology, it's a completely different kind of argument that uses sort of a compactification of the Shimura variety that isn't even an algebraic variety, but is actually a real manifold, known as the reductive Borel-Serre compactification. So this is something that's known when you go to full infinite level at P. It doesn't really use the Hodge-Tate period morphism. It uses perfectoid spaces, but it doesn't need this extra information. However, it turns out that if you want to prove some vanishing at some lower level, so you don't just look at infinite level at P, but maybe you want to consider this kind of ordinary completed cohomology. So for example, when you have a split group and you choose your N0 to be the ZB points of the unipotent radical of the Borel, it turns out you can prove a vanishing theorem even at this lower level, and at sort of all intermediate levels between this one and this one, using the geometry of the Hodge-Tate period morphism. And this is a theorem that I proved together with Dan Glotta and Christian Johansson, and it's based on earlier work with Chi-Yun Su, Lucia Motz, Emmanuel Reinecke, and Sheng-Chi Shi that sort of did some special Shimura varieties, some special cases. And so the assumption here is that you have a Shimura datum of Hodge type, and that the group that gives rise to the Shimura datum is split over QP. And then you can prove that the completed cohomology at this level N0 vanishes above the middle degree when you consider really cohomology with compact support. All right. And so the ingredients that go into this theorem are, first, you need to use p-adic Hodge theory. So you need to use Schulz's primitive comparison isomorphism, which gives you a way of transforming the étale cohomology of the Shimura variety at this intermediate level N0 into cohomology of sheaf I plus mod P at this intermediate level. So there's some comparison theorem. And then you also want to use this vanishing result that I mentioned of basically I plus behaves pretty much like O hat plus would. And so if I knew that the space was perfectoid, I would immediately get some bound. So this kind of vanishing for perfectoid spaces or affinoid perfectoid spaces, which will allow you to replace étale cohomology here with just cohomology with respect to the analytic topology. So there's one ingredient like this that I would sum up as p-adic Hodge theory. But then another ingredient is, has to do with the geometry of the flag variety. And you have to consider a decomposition of this flag variety into maybe called Bruhat or Schubert cells, where you consider decomposition into BQP orbits, and then you get locally closed cells that are indexed by certain elements that are cosets of the Weil group of G. And because I'm considering here BQP orbits, this stratification descends to the quotient of this flag variety by N0. So a priori, my Hodge-Tate period morphism exists at full infinite level. But at the very least, as a morphism onto a topological space, it can be descended to this quotient by N0. And this Bruhat stratification will also descend. And then the final ingredient is that you notice that basically each W, each cell, the preimage of that cell under the Hodge-Tate period morphism at this intermediate level N0 will become sometimes it will be perfectoid and sometimes it will not be, but you can quantify precisely the extent to which it is or isn't perfectoid. In some sense, what you do is you construct perfectoid cover of each cell that is a torsor for ZP. So for some free ZP, ZP to some number of copies of ZP, those number of copies just depend on the length of this Weil group element. So what you do is you quantify when different subsets of this tower become perfectoid. And by doing that, you show that if you consider this I plus just as an almost sheaf, and you push it down under Hodge-Tate, but at this intermediate level N0, and you restrict to one of these Bruhat cells, then you get a complex that is supported in degrees from 0 to D, which is the dimension of the Shimura variety, minus the dimension of this cell. And so because of this, it turns out like a simple argument using a spectral sequence allows you to conclude that the cohomology of this complex is always supported in degrees from 0 to D. And I want to give you a toy model of this because I know it's probably pretty hard to follow in this abstraction. And so I want to give you a toy model for the modular curve. And it basically all boils down to the geometry of the reduction of the modular curve, mod P. So I consider the modular curve at level prime to P. And here I consider the modular curve at level gamma 0, where I've added gamma 0 P into the level. So Iwahori level at P. Moduli theoretically, I have my elliptic curve with whatever other extra structures, and then a subgroup of the P torsion. Or you can write it in a different way as sort of an isogeny of degree P between elliptic curves. And then at this level, the modular curve has two irreducible components. One I've labeled as blue, and maybe one should call it anti-canonical, and the other one I labeled as red, and one should think of it as canonical. And it's essentially the question of whether the kernel of this isogeny is the canonical subgroup or not. And on the red component, the forgetful map to level prime to P ends up being an isomorphism. On the other component, the forgetful map to level prime to P ends up being the relative Frobenius. And maybe I should really say it would be better to remove the supersingular points and really think about it in terms of the ordinary locus. So you have this decomposition, and you already see that there's at level gamma 0 P, there's two components that behave very differently. And turns out when you go up to a tower, a gamma 0 P infinity tower, or a gamma 1 infinity P infinity tower, which is this level N0, there's going to be one component where the transition maps are canonical lifts of Frobenius, and where you naturally get a perfectoid space, and one component where the transition maps are essentially isomorphisms and you stay as far away from perfectoid as possible. Though the geometry of this reduction modulo P matches the Bruhat stratification on the flag variety. So the flag variety is just P1, and the stratification into B of QP orbits is breaking it up as A1, disjoint union infinity. And so what I've sort of tried to explain here about the geometry of the reduction modulo P can be made precise and can be used to show that there is a big component of the modular curve at this intermediate level N0, which is the anti-canonical locus, which is perfectoid. And what I've described here in such a sketchy way, in fact, requires some serious arguments, and this is a result that in this setting is due to Ludwig. So by this, I mean really the pre-image of this entire cell, which is not a quasi-compact open. So it's really A1, the adic space associated to A1, the pre-image of that is perfectoid. And then the preimage of this point is not perfectoid, but it's not that far from being perfectoid. It has a ZP cover that is perfectoid. And moreover, this dimension is very small. This is just a point, so 0 dimensional. So over the one-dimensional locus, you know you're perfectoid, and there you have cohomology just in degree 0. And over this 0-dimensional locus, you have cohomology maybe in degree 0 and 1. But because this is small, you win. So this is a toy model for how you prove the theorem for Shimura varieties of Hodge type. And I just want to say that sort of the key thing that makes it work when your group is split over QP is that I think it's the same reason why the ordinary locus is dense in the special fiber at Iwahori level. And there's a natural way of matching these Bruhat cells and these Weil group elements with components of the ordinary locus at Iwahori level with these so-called Kottwitz-Rappaport strata. All right, so are there any questions about this kind of result for completed cohomology? All right, so now I want to discuss a sort of different kind of result at finite level. And one thing that I want to warn you about is you really want to consider L not equal to P in this setting. So what I've talked about before, it was really a p-adic thing where we're using p-adic comparison theorems and so on. Here, I want to fix my coefficients L, and my prime P is the prime where I consider perfectoid Shimura varieties. And it's really crucial to the method that these primes are different. Okay, and now I'm going to work with a specific Shimura variety to state a theorem. So I want to consider a CM field, which is a composite of a total real field and an imaginary quadratic field, and I want to assume that the totally real field is not Q. And I want to consider a unitary group that preserves a non-degenerate alternating Hermitian form on F to the N. And I want to assume that this the unitary group that you get is quasi-split at all finite places. And then you can take M to be a maximal ideal that is in the support of one of these cohomology groups with mod L coefficients. And for a finite level result, you see one difference even in the level on the level of conjectures. For completed cohomology, you just expect vanishing without caring about Hecke eigenvalues. At finite level, you will always have cohomology in degree 0. And so, or, for usual cohomology. And so because of that, if you really want to prove this kind of vanishing result, you have to put some non-degeneracy assumption on M. And in the conjecture I stated, it was this kind of global thing. The associated global Galois representation is absolutely irreducible. For the theorem that I'm going to talk about, it's going to be a local condition, and it's a genericity condition at an auxiliary prime P that is different from L. This is going to be a condition that maybe I won't state precisely, but it guarantees that all the lifts of my Galois representation, rho m bar, to characteristic 0 will correspond under the local Langlands correspondence to representations that are principal series at P. And so for GL2, for instance, you want to consider something that is, say, unramified at P, and where the ratio of the eigenvalues is not P or P inverse. Okay, and so in this setting, we can prove this kind of theorem. This is joint work with Peter Schulze. It's 2 papers. So the first one treats the compact case. And in that case, you show that, I guess it doesn't matter whether it's usual or compactly supported cohomology, but localized at an M that satisfies this genericity condition, you can show that cohomology vanishes outside the middle degree. And then another case that we treat is one where the group is quasi-split. And in particular, that's going to imply that the Shimura variety is non-compact. The unitary group will have signature NN. Yeah, I guess, okay, I want to consider an even quasi-split unitary group, and the length of the residual representation to be less than or equal to 2. So either absolutely irreducible or at most a direct sum of two absolutely irreducible representations. And in that case, we can show that the cohomology with compact support is only concentrated below the middle degree, and the usual cohomology is only concentrated in the middle degree and above. And of course, if the length is really 1, so the representation is absolutely irreducible, you can actually show that they are in the middle degree. But somehow for certain applications, such as this Caligari-Garrity program, it's important to treat the case where the length is equal to 2 and where this kind of result is the best that you can do. All right, so that's a result. And I want to again just mention what the key ingredients are. So the first thing is you again want to consider the geometry of the Hodge-Tate period morphism, and you want to consider a certain stratification, but it will be a completely different stratification from the one that we considered in the L equals P case. Namely, here you want to consider the Newton stratification. And so you can decompose this flag variety into locally closed strata that are indexed by elements of the Kottwitz set that are admissible with respect to the Hodge co-character mu. And so this is something that will mirror the usual Newton stratification that you see on the special fiber of Shimura varieties. It's exactly the same indexing set, and there's a compatibility between the two on points of rank 1. Okay, so that's one ingredient. Another ingredient is that you can identify the fibers over each Newton stratum with perfectoid Igusa varieties. So these are some more sort of classical objects that are reasonably well understood. And in the compact case, which is really what I'm explaining here for simplicity, the identification of the fibers goes further, and even we really say what the fiber bundle structure is. And the result that we prove is best described as an infinite level version of the Mantovan product formula that describes the relationship between Shimura varieties, these Igusa varieties, and also Rappaport zinc space. Okay, so that's one ingredient. Another ingredient is that in some sense, if you take your coefficient sheaf, which might as well just be the constant coefficients FL with L naught P, and you push it forward under the Hodge-Tate period domain, and you have a Heck action, so you could even localize at a particular system of Heck eigenvalues, then what you get behaves in some sense like a perverse sheaf. And the heuristic is that you should think of I mentioned that in some sense you can sometimes describe an integral map, an integral version of the Hodge-Tate period map. This integral version is basically a profinite morphism that will preserve perversity. So that's the heuristic for why this might behave like a perverse sheaf. But what we need to know is the following. You take this complex and you look at the stratification. Strata here are locally closed. You go to the first the largest dimensional stratum where this complex is supported. And then this vague sentence here translates into a precise statement which says that over that stratum, this complex is supported in 1 degree. That's something that, you would expect perverse sheaves to do when you have a stratification where, for instance, the stalks of your sheaf are constant over a given stratum, which is something that holds true here. Okay, so because you're in 1 degree, it turns out you can lift this to characteristic 0, and that's really something, a subtle point. You can show that it doesn't just contribute to the FL cohomology of the Igusa variety, which is the fiber, but really to the QL cohomology of the Igusa variety. And then you can compute this cohomology using the trace formula, and here most of the work has already been done by Shin. Okay, so one remark that I want to make is that in the special case of Harris-Taylor Shimura varieties, Boyer actually proves a stronger result in the sense that he goes beyond this generic condition. And then if you're not generic, then you expect cohomology to show up in more degrees, and he's able to quantify this in certain instances. But for this particular U1 and -1 Shimura varieties, and using a completely different method from ours. But I guess Koshikawa announced that he can implement, or he can prove Boyer's result also using the geometry of the Hodge-Tate period morphism and building on this method. Okay, so again, what I want to do now is give you a toy model of what happens for the modular curve. So here, this set just consists of two elements, and I've just labeled them ordinary and supersingular. So it's just a question of whether your elliptic curve is ordinary or supersingular. And then you have the following stratification, and I said sort of you have it downstairs because we define it, and you have it upstairs just by pulling back from the special fiber, and at least on the level of rank 1 points, these agree. And so this should be taken with a grain of salt in the sense that it holds on rank 1 points. But so on the flag variety, the ordinary locus is closed and it consists of the QB points. And the supersingular locus is the complement, and it's the so-called Drinfeld upper half plane. All right, and then one nice thing that happens about the fibers that you can really see for the modular curve is that, so at a point on the Drinfeld plane, the fiber of the Hodge-Tate period morphism can be identified with a profinite set, and in fact, it's a Shimura set for D cross. So these Igusa varieties are actually zero-dimensional in this case. You get a profinite set of points, and this can be identified with a Shimura set for D cross, where D is the quaternion algebra that's ramified both at P and at infinity. And for this precise result, you can find it in a paper of Shan Hao. Okay, so because of that, sort of the computation of the cohomology of Igusa varieties becomes a lot simpler in this case, or at least our argument becomes simpler. So any system of Hecke eigenvalues away from P that contributes here comes from some automorphic representation of D cross. And then if you apply Jacquet-Langlands, you see that so it will correspond to an automorphic representation of GL2 of A, such that pi P, the component at P of this automorphic representation, has to be in the image of the Jacquet-Langlands map. So in particular, it cannot be a principal series representation. It can be the Steinberg or it can be supercuspidal. And so because of that, you can immediately see that the genericity condition prevents that system of Hecke eigenvalues to contribute to the complex that is supported over the Drinfeld plane. And because you only have two strata here, once you know that you've eliminated this one, you win. All right, so now I can state just that this idea of using this kind of Jacquet-Langlands in geometric form actually also applies to the case of Hilbert modular varieties. So I come back now to this Shimura variety of abelian type that's associated to this group restriction of scalars from F to Q of GL2. And in this case, this is work in progress with Matteo Tamiozzo. We're assuming L is greater than or equal to 3, and then we're taking a system of Hecke eigenvalues that occurs in the cohomology of one of these Hilbert modular varieties, either usual or with compact support. And instead of genericity, I mean, you can impose this kind of large image assumption, which will guarantee that you can find an auxiliary prime P that does have the genericity property that you expect. And then you can show this kind of vanishing result that either usual or compactly supported cohomology has to only, after localization at M, has to only be supported in degree D. In this case of Hilbert modular varieties, there are older results of Dimitrov that cover the Fontaine-Lefy case, but of course this also works when L ramifies in F and outside the Fontaine-Lefy range. And the key idea is that you can work with an auxiliary prime P that splits completely in F, and instead of computing the cohomology of Igusa varieties using the trace formula, you can use geometric Jacquet-Langlands functoriality that in this setting of Hilbert modular varieties is established by Tian and Xiao. All right, so maybe I'll stop here because I'm out of time.
Thank you very much. As I said, the way to clap would be in the chat, or I can clap. Oh, I see a lot of clap in the chat. That's a sign. And so if you have any questions, please either raise your hand or write them in the Q&A right now. That would be the easiest for us. So there's one question, Anna, about you said for theorem 3 that rho sub m should be generic. Is there a way to relax that?
Well, in this generality right now, not that I know of, but you know, for these Heller-Taylor-Shimura varieties, Boyer relaxes that. Of course, if he relaxes that, he gets cohomology in more than just the middle degree. So in that sense, you know, one could hope that you can relax the condition and you can understand the cohomology more generally, but it's not clear that, yeah, that you would really expect cohomology just in 1 degree if you don't have this kind of genericity at 1 prime. It sort of mirrors this genericity. You should think of it as mirroring temperedness. That would be a condition that you put on, say, the representation, the automorphic representation at infinity in the characteristic 0 setting. That's something that Borel and Wallach compute in this case, that tempered representations contribute to cohomology in 1 degree. And genericity and temperedness, at least for GLN, they're pretty closely related. So, I mean, I don't know that it's really the optimal condition, but it's at least reasonable to believe that it's close to optimal as far as local conditions go.
Thanks. There's another question by Harald Gröbner, who asked, in your theorem 3 on unitary groups, what is the condition F equals F plus times E good for? Is it due to the techniques used in the proof, base change, or in any other sense necessary for the result to hold?
Yeah, it's essentially an assumption here. Sorry, in the techniques that have to do with the computation of cohomology of Igusa varieties. So my guess is that it's not, it's a technical condition that can probably be removed.
And there's
it's not needed for any of the geometric results.
Thanks. And one last question before we go to the break. There's an anonymous question. Is there an easy way to see analogous vanishing for characteristic 0 completed cohomology?
Well, for completed cohomology, if you know vanishing mod p, you know vanishing with z mod p to the n coefficients for any n, and then you know, like, completed cohomology is ultimately defined by taking, that's why I had an inverse limit, because I confused myself with this. But you want to take an inverse limit of the cohomology with z mod p to the n coefficients. The inverse limit now being over n, and then that would be completed cohomology with zp coefficients, and then you want to invert p in that. And so if you show it for mod p, you also get it. Yeah.
Okay, thanks a lot again, Anna. Let's thank her again in the chat. And